The chain rule, this is another differentiation technique in calculus. And the chain rule is used for functions that are in that form where you have f of g of x. So you have one function inside another function. You're not multiplying them, you're not dividing them. It's the composition of two functions with one inside the other. So here are a few examples of where you would need to use the chain rule. So if you look at this first one, you have all this stuff raised to the fifth power. And so in this case, you could say that the outside function, the big function, is x to the fifth power. And inside x to the fifth, you have the function x cubed minus 4x. And so with these problems, you very typically have parentheses to kind of indicate the inside. Number 2 is the same. Inside the tangent function, I have x cubed. And so you could say my outside function is tangent x. And then inside that tangent x is the other function of x cubed. And for exponential functions, these are the ones where you typically do not, or you very frequently will not see parentheses indicating the inside. But for an exponential, I typically see e to the x, and in the place of that x is the function sine x. And so my outside function would actually be e to the x, and then inside that is the function sine x. And so this is what you're looking for that would indicate the need for a chain rule as opposed to product or quotient or some other technique. So the chain rule itself, you do what you would think is the opposite of the order of operations. This is the one time you actually start on the outside and work your way into your function, get to the interior. So we do the derivative of the outside. So we do the derivative of f, leave inside alone, and then we multiply by the derivative of the inside. So it's f prime of g, then times g prime. And it's easier to see that by looking at a few examples. So for number 1, I see all of this stuff raised to the fifth power. And I suppose you do, if you hate yourself, have the option of writing this quadratic 5 times, expanding it, and then doing the power rule. But this is where the chain rule comes in handy. And what you want to do when you're doing the chain rule is you want to identify an inside function and decide what the outside function is. So here in the inside, I see this polynomial, x squared plus 3x plus 1. And on the outside, I'm seeing x, I'm seeing stuff to the fifth power. And when you're doing your chain rule, you start by leaving the inside alone and you do the derivative of the outside function. So I'm over here in thinking land. What if instead of all that ugly stuff, I had just x to the fifth? Well, in that case, the derivative would be pretty easy. It'd be 5x to the fourth. And we leave the x part alone. And that's what I'll do here. So when I do this derivative for number 1, I'm going to start by completely ignoring the x squared plus 3x plus 1. And I'm going to do the outside derivative. I'll bring the 5 down, raise it to the fourth power. So just like 5x to the fourth, only instead of an x, we have x squared plus 3x plus 1. Then we finish by multiplying by the derivative of that inside part. So the derivative of x squared plus 3x plus 1 is 2x plus 3. And you always need to remember that you multiply by the inside of the inside derivative. You do not do both pieces at once. Don't bring the 5 down and the derivative of the inside. You have to very slowly peel your way into your function, starting with the outside, and then we multiply by the derivative of the inside. So number 2, another situation, I don't have actual parentheses, but we do have a radical. And when I'm doing calculus, I would prefer to see that as x cubed minus 4x squared to the 1/2. And it's the exact same structure we just had for that first example. My inside function, I see x cubed minus 4x squared. That is the inside. And then all of that stuff is being raised to the 1/2 power. So in my mind, my very first pass at the derivative is stuff to the 1/2 power. And the derivative of that would be 1/2 times the stuff to the negative 1/2. We just power ruled that. And that's where I start with number 2. So for my derivative, I'll bring down my 1/2. And I will leave the x cubed minus 4x squared alone. Then I'll subtract 1 from 1/2. So I just finished the outside piece. I just did the derivative of the square root function. That is completed. Now I look inside and I finish the derivative by multiplying by the derivative of the interior piece. So that'll be 3x squared minus 8x, and we are done. You don't have to do anything else with that unless there is a bigger question attached to this. But right now we are just making sure we can march our way through the derivative. And when you're doing the chain rule, the best analogy I can think of is it's a lot like eating a blow pop, where the interior is the gum and the outside function is the candy shell. When you eat a blow pop, most people, if you are normal, you eat the entire outside candy shell first, and when that's gone, you then chew the gum or eat the Tootsie Pop, whatever's on the inside. So that's what we do here. We eat the outside first, we leave the inside completely alone, and then once that outside function has been completely dissolved, you then look inside and you multiply by the derivative of the inside. So here's a couple more. Exponential function, e to the x squared plus 1. And this is the time where you most frequently will not see a set of parentheses indicating the inside. So if you need to, put parentheses around that exponent. And for number 3, my outside function is e to the x, and the derivative of e to the x is e to the x. So when I do the derivative of the e part, it's going to be e to the x squared plus 1. We don't change the inside on our first pass. So I just did the derivative of the e part. I left the inside alone. Now I'm going to multiply that. Why did I swap to red? I'm going to multiply that by the derivative of the exponent, which will be 2x. That answer for number 3 is fine as it's written. However, I do recommend that when you do the derivative of an exponential function, if a chain rule is required, I would recommend that instead of putting the 2x on the right side, I would put the 2x before the exponential part. That way, if you have questionable writing, nobody accidentally confuses this 2x for being part of the exponent. So I would put the 2x in the front. If you need to put the parentheses around the exponent to make it a little bit easier to see, you can. But there's your answer for number 3. See, number 4, I have inside x to the 4th. There goes the bell. I have inside, not x to the 4th, inside secant, I have the x to the 4th plus 2 function. So here's my inside, and on the outside, I'm seeing secant of x, and we leave the inside alone. The derivative of secant is secant tangent. So I'm differentiating only the secant part, and then whatever is inside will stay in the place of the angles or the argument for the secant. So for here, for number 4, y prime, I'm going to start with the derivative of secant, which is secant tangent. And you leave the inside alone. You never change the argument of a trig function when you were doing derivatives. So the x to the 4th plus 2 remains the same. And in that step, I just differentiated the secant. I did the derivative of secant, which was secant tangent. I left the inside alone. Now I look inside, and I need to multiply by the derivative of x to the 4th plus 2. And that derivative is going to be 4x cubed. And you only do one 4x cubed because there's only one x to the 4th plus 2 in your original equation. A few people will accidentally do 4x cubed twice because you see 2x to the 4ths in here. However, the original problem only had a single x to the 4th plus 2 on the inside, so we only need a single 4x cubed in the chain rule. 2 more examples. Number 5, cosine squared. This one, at the beginning of calculus, when people are first getting exposed to the chain rule, this one does not look like a chain rule because you don't see any parentheses. However, do remember that a trig function, when it is squared or cubed or raised to an integer power, they typically put the exponent right here. If you need to help you process this derivative, you can rewrite that as all of cosine squared. And now you can look at that and see there is an inside of cosine. That cosine is being squared. So my outside function is stuff squared. The derivative of that is 2 times the stuff. And so number 5, I'm going to leave that inside alone. So it's cosine squared. I'm going to bring down that 2, leave cosine alone, and it is technically to the first power. I'm not going to write that, but 2 times cosine stuff. I have now done the derivative of the x squared component. Now we look on the inside. The derivative of cosine is negative sine x, and you are done. That is your chain rule. There is no need to further simplify that unless there is a bigger question. And right now there are no bigger questions. We're just answering the basic derivative. And then finally, number 6, let's wrap this one up with a tricky question. I will go ahead and rewrite that because I'm not a fan of having radicals when I'm doing calculus. I prefer exponents. So I'm going to rewrite that as tangent x cubed plus 9 to the 1/2. And when you look at this problem, I see an interior of tangent x cubed plus 9, and all of that is being raised to the 1/2 power. So right now, I'm seeing stuff to the 1/2, and the derivative of that is 1/2 stuff to the negative 1/2. That's what I'm going to do first with number 6. So I'm ignoring the interior, and the derivative of square root of something is 1/2 of all of that something to the negative 1/2, and we leave the inside alone. Do not differentiate the inside on your first pass. Right? So now I've done the 1/2 part, the stuff to the 1/2. I have differentiated that exponent. Now I'll look on the inside, and here we have another chain rule. We have a chain inside a chain, because what I'm looking at on the inside now, my inside is the tangent of x cubed plus 9, and there's an interior to that tangent. I have an x cubed plus 9. So now I have a second inside, and I'm going to ignore the x cubed plus 9, and now I'm seeing y equals tangent of stuff. And the derivative of tangent is secant squared, and we leave the angle alone. We leave the argument alone. So now I'm going to multiply. I've done the stuff to the 1/2. I'm going to multiply by the derivative of tangent, which is secant squared, and I will leave the x cubed plus 9 alone, and we slowly peel our way in, slowly working our way in. We did the 1/2 power, then we did the tangent. I still have not done the derivative of the x cubed plus 9. So I differentiated the tangent. Now the derivative of x cubed plus 9 is 3x squared. So I'll add that, or multiply that at the very end. And finally, I have my answer, as ugly as that is, and I definitely don't feel like trying to clean that up. And we are done with number 6. So there are a few examples of chain rule. Just remember, you start on the outside and you very slowly peel your way in, one layer at a time, and make sure you don't bite off and do 2 derivatives at once. Make sure you're doing it one function at a time, starting on the outside, slowly peeling your way in until there is no more interior.